Good morning. In this third lesson of Learning Outcome 10, you will learn how to perform percentage by mass calculations. This fits your MedSec assessment criteria 10.2b. What do we mean by percentage by mass calculation? I'll give a typical example because this is what we shall be learning through this presentation. It will be the first part of the presentation, by the way. Let us imagine that we have a sample of table salt. We're not interested in the mass, it's just sodium chloride. I might be asked, given sodium chloride, what is the percentage by mass of sodium in sodium chloride? Or likewise, what is the percentage by mass of chloride in sodium chloride? Okay, so that is the type of question, that is the type of problem that we shall be addressing in the first part of the presentation. In the second part of the presentation, we shall move a step forward. We shall determine the value of XH2O in a hydrated compound. Okay, so for example, let me give a typical everyday life example in the laboratory. You will definitely come across also by year 9, probably even previously through your science lessons at years 7 and 8 with copper 2 sulfate, the blue crystals. Now the blue crystals are hydrated copper 2 sulfate and the chemical formula is CuSO4.5H2O. So we know that the number of the water of crystallization is 5. Now in this presentation, we shall find out a way. Let's imagine that we did not know it was 5. It is possible, if that 5 was replaced with a little x, to calculate the value of x and arrive at the numerical value of 5 correctly. Okay? We can do this, okay, if we are previously given the percentage by mass of water in the compound. So you do need some basic information to get to the value of x. But we shall address this particular calculation at the end of this presentation. Let us now look at the particular example that we have on this page. But first I'll just explain the bar right at the top, where you have written percentage composition. I'm reading off right from over here, okay? Describes what proportions of the different elements there are in a compound. It's like the share of the mass within the compound, okay? So let me explain myself further by taking into consideration NaOH, sodium hydroxide, caustic soda. Caustic soda has 3 elements, sodium, oxygen, and hydrogen. And we know that the relative atomic mass of sodium is 23, the relative atomic mass of oxygen is 16, and that of hydrogen is 1. I've also put them down over here so that you can be very sure of this. Clearly, the mass weighting, if you like, the share of the mass of each of these elements within NaOH is not 33% each, okay? 33% would be if the relative atomic masses were exactly the same. If sodium had an equivalent relative atomic mass to oxygen and oxygen the same as hydrogen, then the mass weighting, the contribution to the total mass would be 33%. In other words, 1/3 of the mass would originate from the sodium, 1/3 from the oxygen and 1/3 from the hydrogen. But clearly this is not the case because hydrogen is so much lighter than oxygen, and oxygen is even lighter than sodium. So we have to work out the percentage by mass for each of these elements in a fair way that represents their relative atomic mass. And this is exactly what we shall be doing via the next slide. Okay, so now move on to the next slide so that I will explain exactly how to do this. Specifically, let's ask a question. The question is right over here, okay? What is the percentage by mass of oxygen in sodium hydroxide? So we want to know the share in the mass of sodium hydroxide that is related to oxygen, okay? The mass contribution of oxygen to sodium hydroxide. So the first thing that you have to do is that you need to work out the relative formula mass of the compound. This represents your 100% of the mass, if you like. So since sodium hydroxide is NaOH, okay, so I will write that down over here, okay. As you can see from right over here, the relative formula mass must work out to be 23 plus 16 and 1. Notice that since I only have one of each chemical species, there are no subscript 2s or 3s, it's one of each. Therefore, all I have to do is to add the RAM for each element to the others. So I've got 23 for sodium, 16 for oxygen, and 1 for hydrogen, giving us a total of 40. Please make sure that you always have a copy of the periodic table right next to you whenever you're doing chemistry, whether it's in class, whether it's watching a video lesson. It is the essentials of chemistry, okay? So it is the essential item to have right next to you at any time. So that 40 will represent our 100%. Now all we have to do is, if we're asked to find out the contribution of oxygen to the mass of NaOH, we look at the relative atomic mass of oxygen, which we have said is 16 right over there, okay? And we divide it by the 100%. The 100% is the 40 of the total RFM, relative formula mass of sodium hydroxide. And it works out to be exactly 40%. So the percentage by mass of oxygen in NaOH is 40%. You could challenge yourself by finding the percent by mass of hydrogen in NaOH and also by finding the percent by mass of sodium in NaOH. All you have to do is to do exactly this type of calculation, but instead of using the RAM of oxygen, you use the RAM of hydrogen if you are looking for the percent by mass of hydrogen, and you use the RAM of sodium if you are looking for the percent by mass of sodium in sodium hydroxide. Now, one word of caution. Don't let a more complicated formula, something that looks like a bit more complicated, I'm referring to ammonium nitrate. Okay, ammonium nitrate, as we can see over here, is a very important fertilizer worldwide. Indeed, if it weren't for ammonium nitrate and ammonia-based fertilizers, it would not be possible at all to sustain the world's population at the current 7 billion circa mark. Okay, the world's population can only be maintained at such high levels due to the use of artificial fertilizers worldwide. It's also used as an explosive, by the way. There are various uses of ammonium nitrate. The two principal uses worldwide commercially are in the agricultural industry and also in the as in terms of explosives. Well, ammonium nitrate has the formula NH4NO3, okay? And a typical question, which is related, directly related to its use as a fertilizer, by the way, is to find the percent by mass of nitrogen in ammonium nitrate. For those of you who don't study biology, nitrogen is an extremely important element when it comes to plants synthesizing, making up their own plant protein. Okay, so a lack of nitrogen content in the soil will lead to stunted, delayed, or reduced plant growth. Okay, eventually the plant would even die as a result of not being able to synthesize to make up its own plant proteins. Very importantly, the approach is exactly the same as we did with the simpler example for sodium hydroxide. The first thing is to find the full RFM, the relative formula mass for ammonium nitrate, and it's right over here. But watch out for the subscripts this time. go element by element in the order that you see it in the formula. So first of what we're seeing is 1 nitrogen, and you put down the relative atomic mass for nitrogen over there. Next, we've got 4 hydrogens. Now hydrogen has a relative atomic mass of 1, but we have 4, therefore we multiply the 1 by 4. Okay? Actually, I've even in brackets indicated what each relative atomic mass stands for. So in the first case, I have 14, which represents a single nitrogen. I've got 1 by 4, that is actually the contribution from 4 hydrogens. Next, as you notice, we've got another nitrogen. So we put down that contribution over there. And finally, we have 3 oxygens. So since oxygen has an RAM of 16 by 3, that works out to be 48. If you add up all of that together, you have the relative formula mass equivalent to 80. So that is our 100%. Now the question was to find the percent by mass composition of nitrogen in ammonium nitrate. Now, all you have to do is to look at the RAM contribution of nitrogen. You see that nitrogen occurs twice. I have it over here. I'll mark that with a X, and I have it again over there. So you have to do 14 plus 14, that's 28, okay? And you divide it by the 100%, which is the relative formula mass. And the calculation is right over here at the bottom. 28 on 80 all over 100, and it works out to be 35%. In other words, we are saying that ammonium nitrate is more than 1/3 nitrogen, and that's extremely nitrogen rich. This is interpretation of data. You are not just calculating a result, but you're also asking yourself, does it make any sense? If one of the applications is as a fertilizer, okay? Therefore, does it make sense that this compound has 35% nitrogen? And yes, it does make a lot of sense for the very, very simple reason that such a high percent of nitrogen is exactly what is required to fertilize fields and to promote plant growth. Right, I've included a set of four examples. I was going to say worked, but they are not worked. You have to work them out. I will just work out through the first example, and then the next 3 you should do on your own at home. You could decide to print out the sheet, or you could just write them down on a piece of paper and then ask your class teacher to check them for you. Of course, you must have a copy of the periodic table. I will not work out the final answer, but I will show you how to do the calculation. So basically, if you want to find out, so let's go to pen. I will use this time the red text so that it stands out more clearly. Now notice the question, find the percent mass of copper in copper 2 carbonate. You are also given the formula, but please, by this stage of your education, you should definitely know that copper 2 carbonate is CuCO3. Just a quick valency check. Copper 2 carbonate, the Roman numeral 2 shows us that copper has a valency of 2. You should know at this stage also that carbonate, okay, has a group valency. We can also put that in bracket if you wish, although strictly speaking there is no need to do so, of 2. So basically the 2 goes down there when you are converting from valencies of individual elements to final formula, and the 2 goes down there. They cross out so that our final formula for copper 2 carbonate may be written as CuCO3. Good. Now the question is to find the percent by mass of copper in copper 2 carbonate. You should know the RAMs first. So copper will be 63.5. Okay, it could also be found as 64 depending on what version of the periodic table that you've got. Carbon would be 12. Notice I'm not multiplying by anything because there is only 1 of copper and 1 of carbon. However, when it comes to oxygen, as we did in the previous examples such as ammonium nitrate, we then have to multiply the 16 contribution of oxygen by a factor of 3. So then when I find the total RFM of copper 2 carbonate, so the relative formula mass of copper 2 carbonate, okay, that's equal to the 63.5 and our 12, and we've got our 48. So 48, okay, we've got plus 12, so that gives us 60, okay, and we have a 63.5, all right, so that should work out to be 123.5. Or if your periodic table gives copper as 64, it would of course be 124. So I'll put it in as 123.5 based on the RAM of copper that I've included above. Okay. Now, as we did previously, the examiner over here or your teacher is asking you to find the contribution of copper. So all you do is put the RAM of copper there, okay, as your numerator, and the denominator, okay, you divide by 123.5, okay, and since you are being to express it as a percent, as you do in mathematics, you have to multiply that by 100. Now, by inspection, I do not have a calculator over here. I do not wish to waste time in calculating the answer. That is your job to do at home. But by inspection, I can immediately see that I've got 63.5 as a factor of 123.5. It's more, it's just over 50% copper. So copper 2 carbonate is very rich in copper. It's more than 50% copper. And this is the sort of data interpretation that you should be doing each time that you do your quantitative calculations. What does the result actually mean? Does it make sense? What does it tell me about the compound? What does it tell me about elements in the compound? So now you could attempt the second example, excuse me, where you are asked to determine the percent by mass of carbon in potassium carbonate. And as we shall see in the next slide, there are 2 further examples so that you get some practice. Once again, the idea is exactly the same as in the previous slides, okay? And by this time you should have ample practice with finding the percent composition of an element in a compound. Note that in the first example that you are required to work out, you are being asked to find the percent by mass of sulfur in sodium sulfite. Okay, sodium sulfite is Na2SO3. Do not confuse sulfide with sulfite with sulfate. Okay, sulfide is just sulfur, S, sulfite is SO3, and sulfate is SO4. The way I learned it a very long time ago is that sulfate, 8, that means plenty of oxygen. So it's SO4. Sulfite, soft, okay, there's a T sound for table, less oxygen. Instead of 4, I have SO3. Sulfide, the hard sound, okay, well, no oxygen at all, just sulfur. You would remember them much better if you tried these sort of mnemonics, okay? That's the way I still remember them after my A-level chemistry teacher reinforced what I had learned at O-level. And that's a long time ago, okay? Let's look at the fourth example. You have the percentage by mass of oxygen in nitric acid. Once again, I should emphasize the fact that at this stage of your chemistry education, you should definitely know offhand the chemical formula for nitric acid, sulfuric acid, of course, hydrochloric acid, and even, okay, perhaps I'm asking a bit too much, perchloric acid. Perchloric acid, which is HClO4, is another strong laboratory acid. To be fair, it's not commonly found in the O-level classroom, but in the A-level plus, I wouldn't be surprised to meet it. It's a very strong acid, and it's also explosive if not stored correctly. Okay, but it has very, very important applications in the laboratory, at least definitely in research and also routine testing laboratories. So this is the first part of calculating the water of crystallization. This first part is the simpler part, so that it will then lead us to the calculation proper, which I introduced right at the beginning of the presentation, where I said that we will be able to find the number of X of H2O. I'm going to do this stepwise. Let's imagine that we are actually given the formula, okay, magnesium sulfate 7 water. Now, basically this is hydrated magnesium sulfate. Where do we find it in everyday life? Well, it can be found as a medication, okay, that is used, but it wouldn't be in the fully hydrated form. Let me be careful about this. It would be either in the partially hydrated form or in the anhydrous form. It would be found as a paste, okay. Now, if you read the info on the paste, you will see there will also sometimes be an indication of the degree of hydration. It only becomes fully hydrated, which is MgSO 4.7H2O, after having absorbed moisture and water, okay, content from your inflamed area. So it is used to treat skin infections, surface infections, where you have inflammation and there's the accumulation of fluid. So let's imagine you have hurt yourself. It happens very much close to the fingernails or toenails sometimes, okay, and the area gets infected. There is a swelling. Now, in order to reduce the swelling, magnesium sulfate paste, which is sold in little containers from a pharmacy, and it's not cheap at all, okay, it won't be in the fully hydrated form, MgSO 4.7H2O, either partially hydrated or anhydrous. It looks like a white paste. All you do is you spread it out on your finger or on your toe, and what happens is that it will absorb water and get itself to be fully hydrated. Once it absorbs the water, it will reduce your swelling, okay? Now, that is some background about it. Notice the huge difference in appearance, okay? If we're talking about the anhydrous compound, it looks like a white powder, and that is the anhydrous compound. Once it's hydrated, and if you give time to the crystals to form, it appears as white crystals, okay, as can be seen over there. Now, let's get to the calculation. If you are asked to calculate the percent by mass of water in magnesium sulfate 7 water, it's not difficult at all, okay? What you have to do is, once again, find the total relative formula mass for the compound. And the relative formula mass for the compound can be determined as we did previously. Look at each element and note the subscripts and have the periodic table right next to you. I gave you the relative atomic masses that you'll need right over there. Notice that working from magnesium as your first element, we have 1 magnesium, so we put down 24 RAM of magnesium. Next, we have 1 sulfur, RAM is 32. Next, we have 4 oxygens, so I have to do 16 by 4. Next, I have 18. Now, 18 for water, we have 2 hydrogens. Okay, each hydrogen contributes 1, and I have 1 oxygen, which is 16. So a single water molecule has a relative formula mass of 18, but I've got 7 water molecules, so it's 18 by 7. If I do all of that together, it's 246, and that is the relative formula mass of magnesium sulfate 7 water. Now, since I want to find the percent by mass of water in that compound, well, all I do is 18 by 7 works out to be 126. That is the percentage That is the share, that is the share of the mass of the water. So all I do is divide the share of the mass of the water by the total relative formula mass, and as you have over here, you multiply that by 100. The result is 51.2%. So what this means is that the compound magnesium sulfate 7 water is by mass 51.2% water. So the water component is actually a bit greater than the compound itself, than the contribution of the compound itself. Let's now go on to the next final calculation for this presentation. This is the biggest, if you like, the most challenging calculation for this presentation. It also satisfies the requirement of the METSEC assessment criteria that you saw on the initial 2 slides, where you are required to calculate X for the water of crystallization. Now, let's look at the question right at the top. I'm going to do this very much stepwise. I'm going to move exactly in line with each step. I won't miss anything out so that you'll definitely understand this. So you are given over here right at the top the percent composition by mass of magnesium sulfate in the salt hydrate is 48.8%. Let's understand what that means. What we're saying is the percentage composition by mass of MgSO4. MgSO4 is 48.8% of the total mass given the formula MgSO4.xH2O. If I have that information, I can calculate what X is. Okay, and in fact what we're given is derive the formula of the compound. In other words, we're being asked to calculate X. Is X 1, 2, 3, 4? Okay, all we're given is that the MgSO4 component, the anhydrous component, if you like, okay, the MgSO4 component contributes to 48.8% of the total mass. Now, what does this immediately tell you? If MgSO4 is only less than half the mass, doesn't it tell you that there must be a lot of water of crystallization? So you definitely don't expect H2O to be 1 and neither 2 and neither 3. It probably is fully hydrated. And you should know from your background chemistry that fully hydrated means 7. So I would expect the MgSO4, even at this stage, to be MgSO4.7H2O. That's not cheating, that's knowledge. Okay? Now we'll confirm my prediction. Okay, so how do you go about this? Okay, of course you don't put in 0.7H2O immediately, you have to prove it by calculation. So the first thing that you do is you calculate the relative formula mass for your compound with the information that you have so far available. What we do is, since we do not know the water of crystallization is, we put in an X. X stands for the number of the water of crystallization. And we calculate the RFM just as if it were an algebra problem. So once again, I do know that I have 1 magnesium, 24, 1 sulfur, 32. I have 4 oxygen, 16 by 4. When it comes to water, we know that the relative molecular mass of water is 18. 16 from the oxygen and 2 from your 2 hydrogens. But I do not know how many water molecules there are within the hydrated magnesium sulfate. So I multiply that 18 by X. So my relative formula mass for my hydrated magnesium sulfate is represented by 1,2,0 plus 18X. And this is the relative formula mass. I will write it over there. Okay. For, okay, your MgSO4.xH2O. Okay. Now, let us now go to how we shall determine X exactly. You should agree at this point that 120 plus 18X represents the full relative formula mass. So it's 100% of the mass, if you like. What we are given is that the MgSO4 component is only 48.8% of the mass. So the remainder, 51.2%, okay, should represent, of course, the water component, okay? So we can work it out fully in this way. If I have 120, okay, 120 represents the relative formula mass of MgSO4 all over 120 plus 18x. So if I express the relative formula mass of magnesium sulfate as a fraction by dividing it by the full relative formula mass, we get 48.8%. Isn't that what we said over here? The percent composition by mass in the first line of MgSO4 in the hydrate is 48.8%, so that's exactly what I'm doing over here. I am saying that by dividing the relative formula mass of MgSO4 alone, the 120, I divided by the whole of the hydrated compound, well, that is 48.8%, okay, which is over here, okay, I'm referring to this line over there. So, in other words, by simple mathematics, if I had to do, if I had to just flip them around, 120 on 18x all over 120 would be equal to 100 all over 48.8. What have I done here? What I've done is I've just inverted them, okay? And you shall see why. I wanted to make 120 plus 18x the subject of my equation. So what I did was I flipped them round. It's fair, you can do that, as you should know from your mathematics. So 120 over 120 plus 18x, I flipped around, so I got 120 plus 18x all over 120. Likewise, I did on the other side. Since I did it on the other side, the calculation is correct. The 48.8 on 100, I flipped around to get 100 on 48.8. Now we make 120 plus 18x the subject of our equation. How do we do this? By multiplying the 120 which is beneath it, all right? So the 120, okay, so if I had to write it over here to clarify my meaning, okay, perhaps it's easier if I rewrite it. So I will rewrite it right over here. So what we've got is this, okay? I've got 120 plus 18x all over 120, all right? And that is equal to 100 all over 48.8. Now, let's see where the pen has gone. Okay, we got it, 48.8. Now, all I have to do next is to bring this right up over there. So then my calculation becomes the one you're seeing over here. Okay, notice I have 120 plus 18x, the subject of my equation, as it is over there, and that is equal to, as I have here, 120 multiplied by 100. Notice what I have also over here, 120 multiplied by 100 all over my 48.8, as I have over there. So when I work all that out, I get 120 plus 18x, you should have a calculator next to you, is equal to 245.902. Notice that we are getting to an algebraic problem solution, okay? It is very easy now to guess what's next. You make 18x subject of your equation as you do in maths, okay? 18x is equal to 245.902 minus 120. 18x is 125, so x is, of course, 125.902 all over 18, which works out to be exactly this. Now, one word of caution. Do not think that you have a mistake. It will not work out necessarily to be exactly 7. All you have to do is to round it off to 7. 6.995 is 7. It's no other number. Okay? So your result is X. The number of the water of crystallization in MgSO4.7H2O is actually 7. Now, I strongly suggest that you do two things. One, replay this video slide another time. Then ask your class teacher for other questions similar to this. Okay, there are also, you could also ask your class teacher to help you out with perhaps also any sample questions that are already being made available by METSEC. Okay, METSEC is already making available sample examination papers to give you an idea of how you shall be assessed in your controlled assessment, in your written assessment examination. Thank you for watching all the video. Okay, it's over, and this gives you a good idea, I should guess, about how to calculate percentage composition of an element in a compound, and also to determine the number of the water of crystallization. Thank you and have a fine day.